In the previous lecture, we were discussing about the stagnation properties. Stagnation properties have been defined based on certain specific processes, but as soon as you evaluate those properties, you can use those properties as properties corresponding to a specific thermodynamic state, disregarding the process by which that state has been attained. For example, when we say that the stagnation pressure is P0 or stagnation temperature is T0 or stagnation density is rho 0, we do not essentially mean that the fluid is physically brought to rest at that particular state. What it essentially means that had the fluid been in a hypothetical process brought to rest at that particular condition, then these would have been the properties, the respective pressure, temperature and density of the fluid at that state. But at any other given state, you will always have a corresponding stagnation pressure, stagnation temperature and stagnation density. So, these are corresponding properties in a sense that every state will be associated with a corresponding P naught, T naught and rho naught. And the important characteristic of this is that P naught by P will be a unique function of the Mach number. T naught by T will be another unique function of Mach number and rho naught by rho is another unique function of Mach number. So, these functional relationships define these properties as a function of the local properties and the Mach number. Now, I would like to discuss 2 points very critically. First of all, why are stagnation properties so important? So, in compressible flows we are referring to stagnation properties with a lot of emphasis. Why we are doing that? So, if you clearly see that, for example, let us talk about stagnation temperature or stagnation enthalpy. So, how we have derived the stagnation enthalpy? So, we have started with the first law of thermodynamics, applied an adiabatic process with no work done. So, you have H is equal to H naught. So, H plus U square by 2 is equal to H naught, neglecting changes in potential energy. From here you will get an expression for T as a function of T naught, which is this one. So, the special factor is that if you go to another point in the flow, if it is adiabatic, let us say it is point 1, for the point 2 you can also write this, for the point 3 in the same flow you can write like this. In this way, for all points in the adiabatic flow field you can write this. Therefore, what remains constant for all points in an adiabatic flow field is the stagnation enthalpy or equivalently the stagnation temperature. Okay. So, stagnation property is a reference property that remains constant under certain conditions. I will tell you another very subtle thing. Stagnation temperature we can see remains constant if there is adiabatic flow without any work transfer and with negligible changes in potential energy. What about stagnation pressure? So, for stagnation pressure we have used this formula to relate the stagnation pressure with stagnation temperature. When is this formula applicable? This formula is applicable when the process is both reversible and adiabatic. So, this demands only adiabatic with no work done. This formula demands reversible plus adiabatic of an ideal gas, reversible plus adiabatic both correspond to ideal gas. So, ideal gas I am not writing, in a sense that when you write enthalpy in terms of temperature with Cp as constant, what you are essentially treating is not just ideal gas, but ideal gas with constant Cp and Cv, which is called as calorically perfect gas. So, calorically perfect gas is the condition based on which from here you will get this expression for T0 by T, that what we have derived. If it is an ideal gas but not calorically perfect gas, we will get a different functional relationship, but still T0 by T a function of unique function of Mach number, because the whole difference is when you write dH you write Cp dt. This is true for any ideal gas. This Cp is a function of T only for an ideal gas. For calorically perfect gas this is a constant, that is the only difference. So, you will get a function of T0 by T is a function of Mach number. So, T0 by T is some kind of function of Mach number. A special version of the function that we have derived is for calorically perfect gas, but the major assumption that goes behind in addition to ideal gas is that it is an adiabatic process. This is reversible and adiabatic process. So, there is a subtle difference between the definition of stagnation pressure and stagnation temperature. Stagnation temperature is physically the temperature which can be attained by a fluid which is adiabatically brought to rest under no work transfer and with negligible changes in potential energy. On the other hand, stagnation pressure is the pressure which can be realized if the fluid is brought to rest in both reversible and adiabatic process. So, reversible comes into the picture because of this. So, to summarize, we have discussed about the significance of stagnation properties and the subtle difference between the paradigms in which we define the stagnation pressure and the stagnation temperature. So, with this little bit of discussion that follows the derivations of the previous lecture, let us work out a problem. So, there is a reservoir which we call as simply a tank, large tank basically. where you have air at 30 degrees centigrade and the pressure here is P tank. There is a exit to the tank from which air is exiting at 235 meter per second. The temperature is T exit, which is not known. Pressure is P exit, which is not known, and of course the Mach number is M exit, which is also not known. So, you have to find out these three parameters, given that if you have this manometer with a manometric fluid mercury, this is Hg, then the corresponding manometric height H is given as 30 meter and density of mercury is 13550 kg per meter cube. Okay. Now, first let us try to understand the physics of this problem before we solve this. First of all, from the picture itself, it should be clear that the pressure here is greater than the pressure here. That is why the mercury is more subdued, because of the greater pressure. Question is, why is the pressure greater here? So, the condition here corresponds to which condition? The condition here corresponds to this condition, this line condition plus rho air into H into G. So, this line, this center line, this line corresponds to pressure here within the tank. In a connected system at the same level, pressure is same everywhere. So, inside the tank here also the pressure is the same. So, what is that pressure? That pressure is nothing but the stagnation pressure, because the fluid within the tank, well within the tank, is under a condition of absolute rest. So, we can safely presume, of course, you have to make certain additional assumptions that there is the process, so there is perfect insulation, there is no heat loss across the tank and all this. So, if you assume that, then the pressure within the tank is P naught, whereas the pressure here is P exit. So, now we can say, because the condition within the tank is the stagnation condition, we can say T naught is equal to 273.15 plus 30, this much of Kelvin. Now, if you apply the energy equation between the tank and the exit, basically the first law of thermodynamics. So, T tank, so let me write in terms of enthalpy, that is much better. So, T tank, or I wish to write it in terms of enthalpy. So, H tank equal to H exit plus U exit square by 2. Assuming an adiabatic process taking place. So, if that be the case, we can say that this is H naught, which is Cp T naught, and this is H exit, this is Cp T exit. So, we can get a relationship between T naught by T exit, right. So, U exit is given (235 meter per second). So, because U exit is given, from here you can find out what is T exit from this equation. So, let me tell what is the answer. The answer is 276 Kelvin, maybe with some decimals, I am neglecting the decimals. How do you find out the Mach number at the exit? So, how do you find out the Mach number at the exit? So, the sonic velocity at the exit is this one, root over gamma r T exit, gamma is 1.4 for air. So, the Mach number at the exit is equal to U exit by C exit, right. If you calculate this, this is 0.706. So, we have calculated T exit, we have calculated M exit. Now, what remains is P exit. So, we have a formula which we have derived for P0 by P, right. So, what we derived is P0 by P is equal to 1 plus gamma minus 1 by 2 m square into to the power gamma by gamma minus 1. So, this you can get from the previous day's notes, what I am gathering. So, you will get this as P tank by P exit if you substitute M equal to M exit. Okay. Now, there is a difference between, so P tank and P exit, what is that? So, you consider the pressure at this level, at this dotted line, this line. So, you have pressure here is what? P tank. Then what is the pressure here? P tank plus H rho air G. So, that is the pressure here in along this line. Because it is a connected system with the same fluid, pressure at this cross point and pressure at this cross point should be the same. So, at this cross point what is the pressure? That is pressure which is coming from here, that is P exit, because P exit is P atmosphere. So, this is P exit plus H. So, here the pressure is P exit or P atmosphere plus this much H rho Hg into G. So, you have one equation here relating P tank and P exit and another equation relating P tank and P exit. So, by eliminating P tank in these two equations you will get what is P exit. So, P exit is 101 kilopascal, which is for all practical purposes is the standard atmospheric pressure, and P tank if you calculate it just for interest, although it is not asked as a question, or if we ask it as a part of the question, then P tank has to be obtained, it is 140.8 kilopascal. Okay. So, we have worked out a problem that relates the stagnation properties. Next, we will study a very interesting topic in compressible flows, and I would say that this happens to be the heart and soul of compressible flow, that is compressible flow through a variable area duct by one dimensional treatment. One D analysis. So, why I am emphasizing on 1D analysis is because the area is variable, you will have essentially two velocity components coming into the picture. So, strictly speaking it is not a one dimensional flow. For example, if it is an incompressible flow, so let us say that the velocity at section 1, uniform velocity is u1, one dimensional means you can assume uniform along the other direction, and uniform velocity along section 2 is u2. For incompressible limit you have a1 u1 is equal to a2 u2, because a1 is different from a2 because it is variable area. So, something like this maybe, where a is a function of x, because a1 is different from a2, u1 is different from u2, right. So, that means you have a del u del x. Because you have a del u del x which is not equal to 0, for incompressibility you also have del v del y which is not equal to 0, because this plus del v del y equal to 0. For we are discussing everything about incompressible flow, because I want to bring a perspective of the difference between incompressible flow through variable area duct and compressible flow through variable area duct. So, if this is not 0, then this is also not 0, that means you have a V, right. So, then this one dimensional treatment is something which is very hypothetical. Moreover, for compressible flow you have additional constraint. What is the additional constraint? These equations themselves do not work. So, because these equations themselves do not work, the intuitive idea that we always carry with us, and this is a very dangerous intuitive idea, that if area decreases the velocity increases. So, I have over my reasonable long experience in teaching fluid mechanics seen that in an examination or written or oral whatever, if I ask a student that if the area of cross section increases, will the velocity increase or decrease? So, this question everybody answers from intuition that area into velocity, or if the velocity is varying then it is average velocity, area into average velocity is constant. Therefore, if area decreases velocity increases and vice versa. Here the student does not keep in mind that actually area into velocity is volume flow rate, and what is fundamentally conserved by continuity is mass flow rate and not volume flow rate. For a case where density is constant, the volume conservation and mass conservation are identical, because the the mass conservation is rho a u equal to constant instead of a into u equal to constant. So, area into velocity is volume flow rate, that into density is mass flow rate. Remember, although we are not putting a u bar at the top, but this is average velocity. Keep in mind, when we are converting a 2-dimensional problem into a 1-dimensional problem, the velocity that we are essentially dealing with is the average velocity, the velocity integrated over the section. So, here if the area decreases, the velocity may increase, it may decrease, it may even remain constant, you do not know. All is controlled by the bandmaster density. The density is like the bandmaster, which essentially controls that given you change area, how will the velocity respond to it. And the control of density is via which parameter in compressible flow? It is via the parameter Mach number, because if the control, the change over density, the change of density is implicitly related to the Mach number. So, if the Mach number is small, possibly the intuitive answer is correct, that if area is decreasing, velocity will be increasing, but if the Mach number is not small, there will be a physical correction in addition to the mathematical understanding. Physically there may be a different paradigm, that we can see that area is decreasing and velocity is also decreasing, because density is increasing tremendously. So, density plays a very important factor for compressible flow, and therefore, for compressible flow we cannot trivially presume that if area decreases velocity increases, or if area increases velocity decreases. And then based on this there is a third intuition about pressure. So, we normally have a mindset to apply Bernoulli's equation anywhere and almost everywhere, despite conditions occurring under which it is not valid. This has been sort of inbuilt within many of us from the school days, at which we in the first level of fluid mechanics of fluids in the school level, we have been introduced to the Bernoulli's equation in high school. So, when you are talking about Bernoulli's equation, you have to keep in mind that there are several assumptions. One important assumption is that it is a frictionless flow, and the other very important assumption related to compressibility is that it is also considered to be a constant density flow. So, when you write P plus half rho u square is equal to constant, then you are presuming that rho is constant, which for a compressible flow is not true. So, the first error is that if area increases, velocity decreases, that much we cannot say, and the second error is from this equation, if velocity decreases, pressure will increase, that trivial conclusion also we cannot make, because this equation itself is not valid for compressible flow. Even for frictionless compressible flow this is not valid, because this is for frictionless flow in addition to rho equal to constant, and of course steady flow, steadiness we are assuming. So, I am not talking about it over and again, but the important factor is that just frictionless flow is not good enough. You also have to consider whether density variation is there or not. If density variation is there, we cannot use the Bernoulli's equation. So, for frictionless flow with density variation, instead of this we will use the Euler equation. So, to summarize, flow through variable area duct offers with a very interesting proposition of fine tuning the velocity in tune with the density variation in compressible flow. That paradigm of varying the flow features via density variation, that possibility is not available with us for incompressible flow. Let us stop here today. We will continue with the variable area duct analysis in the next lecture. Thank you.